Hi students, this is the fourth lecture session on the subject Operating System Design Module 1 for MTech students. I'm Seema Safar, Assistant Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. The contents of today's lecture session include buffer cache, buffer headers, the structure of the buffer pools, and various scenarios for retrieval of a buffer, how to read and write in disk blocks, and finally, advantages and disadvantages of the buffer cache. Let's begin the session. First, we'll start with the buffer cache. The kernel could read and write directly to and from the disk for all file system access. So it tries to minimize the frequency of disk access by keeping a pool of internal data buffers, and that data buffers are called as buffer cache. When you're trying to read a data from the disk, the kernel will be attempting to read from the buffer cache. If the data is already in the cache, the kernel does not have to read from the disk. Now, what if the data is not in the cache? If the data is not in the cache, the kernel will be reading the data from the disk and they'll be caching it. And they make use of some standard algorithms to save as much as good data in cache as possible. A buffer consists of two parts, which is a memory array and a buffer header. This picture depicts a buffer header. The buffer header contains a device number field and a block number field, as you can see in the figure. This specifies the file system and a block number of the data on the disk, and they uniquely identify the buffer. Then we have a lot of pointers, as you can see in the figure. A buffer head also contains a pointer to a data array for the buffer, and the size must be at least as big as the size of the disk block. Then you can see a status field which summarizes the current status of the buffer. Now let's discuss about structure of the buffer pool. The kernel caches data in the buffer pool according to least recently used algorithm. Now, kernel maintains a free list of buffers that preserves the least recently used order. The free list is a doubly linked circular list of buffers with a dummy buffer header which marks its beginning and end. This figure depicts what I've said now. As you can see here, every buffer is put onto the free list when the system is booted. The kernel takes a buffer from the header of the free list when it wants any free buffer. But it can take a buffer from the middle of the free list if it identifies a particular block in the buffer pool. In both cases, it removes the buffer from the free list. As the kernel removes buffer from the free list, a buffer with valid data moves closer and closer to the head of the free list. This is what you see in this figure. Now this figure is taken from your textbook, which is cited in the reference section. Therefore, the buffers that are closer to the head of the free list, it have not been used as recently as those that are further from the head of the free list. That is what you should note. When the kernel accesses a disk block, it searches for a buffer with the appropriate device block number combination. Rather than searching the entire buffer pool, it organizes the buffers into separate queues, which is hashed as a function of the device and block number. The figure depicts buffers on hash queue, and the figure is taken from your reference text cited in the reference section as number 1. The number of buffers on a hash queue varies during the lifetime of the system. The kernel must be using a hash function which distributes the buffer uniformly across the set of hash queues. Now, usually system administrators will be configuring the number of hash queues when they are generating the operating systems. As you can see in the figure, the headers of the hash queues are on the left side of the figure, and the squares on each row are the buffers on a hash queue. Therefore, the squares which is marked 28, 4, 64, they'll be representing buffers on the hash queue for block number 0 mode 4. Now the dotted lines between the buffers represent the forward and backward pointers for the hash queue. Okay. Now the figure identifies blocks only by their block number, and a hash function is dependent only on a block number which is being used. Hope this is clear. Now let's discuss about various scenarios for retrieval of a buffer with the help of an algorithm for buffer allocation. All these 5 scenarios are listed in this algorithm. As you can see here, if buffer is busy, it moves on to scenario 5. It's marked as scenario 5, then scenario 1. I'll explain each scenario which is mentioned in this algorithm. Now, when kernel tries to allocate a buffer for a disk block, they make use of a get block algorithm. The kernel finds the block on its hash queue, and that is scenario 1. And they'll be marking the buffer busy, and they'll be removing that buffer from the free list. So that is shown as scenario 1 here. Then scenario 2 is in case where the kernel cannot find the block on the hash queue, so it will be allocating a buffer from the free list. Then we have scenario. Here you can see scenario 3. The scenario 3 is a condition where the kernel cannot find the block on the hash queue, and in attempting to allocate a buffer from the free list, as in scenario 2, it finds a buffer on the free list which has been marked as delayed write. So the kernel must write the delayed write buffer to disk and allocate another buffer. That is scenario 3. Alright, now scenario 4, what it says is that the kernel cannot find the block on the hash queue and the free list of the buffer is empty. And the 5th scenario is that the kernel finds the block on the hash queue, but the buffer itself is currently busy. These are the 5 scenarios when you are trying to retrieve when you are trying to allocate a buffer. Hope it's clear. This algorithm depicts how to read a disk block. The kernel checks if the first block is in the cache, and if it is not there, it invokes the disk driver to read that block. If the second block is not in the buffer cache, the kernel instructs the disk driver to read it asynchronously. Alright, then the process goes to the sleep awaiting the event that input-output is complete on the first block. When it awakens, it returns the buffer for the first block, and it does not care when the input-output for the second block has completed. Now, when the input-output operation for the second block has completed, the disk controller will be interrupting the system, and the interrupt handler will be recognizing that I/O was asynchronous, and they'll be releasing the buffer. If it is not going to release the buffer will remain locked and therefore inaccessible to all the processes. Later, if the process wants to read the second block, it should find it in the buffer cache. This is how reading in a disk block is done. Writing in a disk block is depicted in the figure as you can see here. Now what happens here is that the kernel will be informing the disk driver that it has a buffer whose contents should have to be written. If the write is synchronous, the calling process goes to sleep, awaiting input-output completion, and they'll be releasing the buffer when it awakens. But what if the write is asynchronous? The kernel starts the disk write, but it does not wait for the write to complete. The kernel will be releasing the buffer when the I/O or the input-output operations are completed. This is how it works. The last topic for the session is advantages and disadvantages of buffer cache. The use of buffers, it allows uniform disk access because the kernel does not need to know the reason for the input-output operation. And the system places no data alignment restrictions on user processes doing input-output because the kernel aligns data internally. Use of buffer cache, it can reduce the amount of disk traffic, thereby increasing overall system throughput, and it will be decreasing the response time. The number of buffers a system can profitably configure is constrained by the amount of memory that should be kept available for executing processes. Now, the buffer algorithms help to ensure file system integrity as well. And the reduction of the disk traffic is important for good throughput and response time. And the use of buffer caches requires an extra data copy when reading and writing to and from user process. By this, we come to the end of this session. The reference textbooks are listed here. Thank you.